Today's lesson deals with perpendicular bisectors. So we're going to learn about perpendicular bisectors. These are words that we've discussed in the past, but now it's applying them to pictures. So the first thing that I want you to be able to do is draw this type of triangle. So this is the simplest type of triangle to draw perpendicular bisectors on. It's acute and possibly even scalene. So acute triangles are the easiest on all these sections we'll be doing. We like acute triangles. Whenever we're drawing perpendicular bisectors, we have to pay attention to two things. The first step we always have to do is we have to bisect each side. What's it mean to create a bisector? We look at a side, we create a midpoint, we have to put its marks to prove it's a midpoint. By creating a midpoint, we've bisected that side. So first, draw midpoints. Second step, from that midpoint, I'm going to come off of that side perpendicular. That means I want to draw a 90-degree angle coming off of that side where I have the midpoint. So it's going to look something like this, straight off of that side. As long as that's a 90-degree angle, I'm all good. So this is the second step. The second step, once again, we draw a perpendicular segment. Next, I want to continue this process for the other side. So once again, I go back through, I draw my midpoints on another side. So I'm going to go over to this side over here. I'm going to draw a midpoint. I'm eyeballing it, so it's not going to be perfect. I'm going to draw my segment marks, my congruent tick marks. On that side, what do I need to draw next? A perpendicular segment from that midpoint. So I come off of this segment perpendicular. Remember, I'm eyeballing it, so I'm not being perfect. So I now have two perpendicular bisectors on my picture. One key thing to notice, this one I went ahead and I went all the way across and hit the other side of the triangle. I don't actually have to go that far. That's not critical. It's not important. I don't have to go all the way to the other side. I can stop a little short. My key thing that I want to see is where do they intersect each other. Now I'm going to repeat this process for the third side. I go to this third side. What's my first step? Midpoint. Draw my congruent tick marks. Then my segment coming off of that side. Now, obviously mine is not perfect because this is not a perfect right angle. So I'm going to teach you later on how to make better right angles, and I'm going to teach you how to measure the sides to make sure you have the exact midpoint. So we can always measure a side with a ruler to find the exact midpoint. That's going to be one of our tasks later on. I'd measure that side to find its midpoint and this side to find its midpoint. To make a 90-degree angle, I like to use a corner of a piece of paper because it's always a 90-degree angle. So I would slide that corner of a piece of paper right into here and make sure that's truly a 90-degree angle. I would do that for all of these angles. This is the one that is definitely obviously not a 90, and I would say this one as well is not a perfect 90, but it should get you the concept. So these three pieces are called perpendicular bisectors. I've drawn 3 perpendicular bisectors and they are all blue. The neat thing, here's the neat property that occurs. So this point where they cross is called the circumcenter. So that point right there is called the circumcenter. That's this word. The circumcenter is where these perpendicular bisectors cross. This is an answer on one of our activities or quizzes later. This is on your test. I'm going to say, when the perpendicular bisectors intersect, They intersect at a point called the circumcenter. Specifically, it's called a point of concurrency. This is a point where they all cross. Point where the special segments cross. They are concurrent if they cross. And the last part is equidistant. So I'm not going to draw any more in this picture because I want to keep that clean. What I will do, though, is I'll create a duplicate right up here in this section. It's not going to be a perfect duplicate, but I just want you to get the idea. Here's the idea. Where they cross is that point called the circumcenter. So I'm going to draw that kind of in that same area. And actually it would be over here because I drew this point. It should have been over here. So it would be slightly over here. Not exactly in the middle, so don't think of it being in the middle. It's slightly off the middle. If it was equilateral, it would definitely be in the middle. So the neat thing, if that point is called the circumcenter, then we have some interesting facts that occur. These distances will be the same from a vertex to that point. Those three distances will be the same. So from this point to a vertex will be the same. So the segment from the vertex, I'll say vertices, to the circumcenter will be the same. If those are the same, then that point is equidistant from the three vertices. So when those segments are the same, this point right here, the circumcenter, is equidistant from the three vertices. This point is equidistant from the three vertices. That's a major fact that you have to be able to do on these pictures. Next up, we're going to see some simple facts about perpendicular bisectors. How do I know these are perpendicular bisectors? We see perpendicular and it's bisected. I can tell that by the two congruent tick marks. The next part we have to be able to do is understand what's actually going on. So I'm going to do this short phrase right here. If CP, line CP, is the perpendicular bisector of segment AB, then CA, this distance right here, is equal to what other piece? CB. And see, a lot of times you can see that without doing any math or knowing any special properties. This one's pretty simple too. I'm just going to do the short version. If DA is equal to DB, yes, we have that, then D lies on the, if you extend this out, this piece is called the perpendicular bisector. So one more time. If AD and BD are equidistant from that point, then when I extend CP, this CP is the perpendicular bisector. So D would be on the perpendicular bisector. Example 1 is super simple. Key thing, it says AC is a perpendicular bisector. So I'm going to go back through and I'm going to make sure that things match what is given. If AC is the perpendicular bisector, I got to make sure that's drawn on the picture. Is it indicated on the picture? Do I see any perpendicular marks? Where should I add them? Near C? Yeah, right there. So there's perpendicular now. Now I need to also show that it's a bisector because they told it was given. What should I do to show it's a bisector? Yeah, tick marks on BC and CD. Now it's truly a perpendicular bisector. So this right now looks just like some of those postulates and theorems we just discussed. Whenever you have a perpendicular bisector, BA will be equidistant to AD. If those two pieces are equal, I can set them equal to each other. So AD is congruent to what? AB. They're equal to each other. How long is AD? What's the expression for AD? 4x, and AB is 7x minus 6. Some people struggle a little bit with solving this. Typically, I do say move the smaller x first when we're doing algebra. However, when I move this x, I'm left with nothing on this side, so I probably wouldn't do that in this case. So I would move the other x term away from the number. So I would subtract 7x from each side. That way they'd cancel. 4 minus 7 is negative 3 with an x. And now I can easily get rid of that negative 3 by doing what? Division. Divide by negative 3. And negative 6 divided by negative 3 is positive 2. Does it say find x? No, so there's one more step. So I need to substitute in for AD. So AD is right here. AD is 4x. But I can replace the x with what term? 2, yeah. I can replace it with 2. So 4 times 2 is 8. There's my final answer right there. Example 2. This one comes through and says in the diagram, line KM is the perpendicular bisector. Is that noted? Is everything perpendicular and bisector? Do I have perpendicular? Yes, it's noted right here. Do I have a bisector noted? No, I need to note that. Where should I note that? JNNL. Now it's a perpendicular bisector. And once again, that was given to us. So it says, what segment lengths in the diagram are equal? So obviously, JN and NL, so I'd write those to the side. JN is equal to NL. Since it says equal, I don't need to put the segment symbols on top. If you did it, I wouldn't mind too much. What else is equal? JK, KL. JK and KL. And one other piece. JM and LM. All right, so that one's done. We got A done. We're now on B. Is M on line KN? Is this point going to lie on this line whenever it's extended on out? Yes, why? Yeah. Yep, because JM and LM are congruent, they're equidistant from that same point, then it will be on the perpendicular bisector. And that's one of the properties we just learned a little while ago. Try these two checkpoints. They're pretty quick, pretty simple. On checkpoint number 1, it says, what segment lengths are equal? So which one did we say are equal? I would definitely say FG is congruent to FH. That would be my first one that I would say because it obviously gives you the numbers. FG is equal to FH. Any other pieces I can say are congruent? GJ. So that's here. And JH. Because they're equidistant to the same point. It's on the perpendicular bisector. These are the same because they give you the numbers. Any other piece? Yeah, GK and KH. Good. And since this is true, I can set up those two equal to each other. So put those marks, and now you can set those equal to each other. 2x equals x plus 1. Subtract x from each side. You get x is 1. Do I stop there? Make sure to read. It says find GH, so I'm going to take that. I want the whole length. I want the whole thing. So one thing I would do is I would take it and plug it in here. 2 times 1 is what? 2. So this piece is 2, so that piece is 2, and 2 plus 2 is 4. So GH is 4. Theorem 5.4 just talks about perpendicular bisectors and what pieces are congruent. In that picture, which pieces are equal? In this picture up here, which pieces are equal? Yes. No, they're not all equal. Only certain ones. A what? Okay. AF, FC. Okay. BA and DA, so I'll put doubles there. BE, EC. Okay. There's a little bit more. Here's where people start getting confused. Those are midpoints. These are all midpoints. That's why those occur. But it does tell us we do have a perpendicular bisector. I'm missing something really important. I need those 90s. So truthfully, this blue piece is a perpendicular bisector. That one's a perpendicular bisector, and this one. These pieces are not equal unless it's an equilateral triangle. There are different parts, and we wrote this down. Under your definition for equidistant, we wrote which pieces are equal. From where to where? Yes. From the vertex to the circumcenter. Vertex to circumcenter. Each of these green pieces are going to be equal. And I'm running out of marks. I guess I should do 4. Those 3 are the important congruent pieces. They're equal to each other. And we wrote that down. We said when perpendicular bisectors are formed, the distance from the vertex to the circumcenter will always be the same. It's not the perpendicular bisectors the same. So be careful there. A common misconception is that those triangles inside are congruent. That's not true. It's only true on special types of triangles. So don't try to say that all these triangles are congruent. That would only work on special types of triangles like equilateral and stuff like that.